All right. So in lecture 4 of strength of material 1, we want to look at analysis of bars of varying section 2. Okay. In section 1, we looked at prismatic section, but in section 2, we want to make our main focus be on non-prismatic section. Okay. Very good. Our lecture outline. Our lecture outline is composed of 1, the introduction, uniformly tapering circular section, also uniformly tapering rectangular section, and some work examples as well. In our introduction, 1, that is in lecture 3, we learn about how to calculate stress, strain, and axial deformation of prismatic and non-prismatic members. We also learn about how to draw free body diagram of a given problem for both prismatic and non-prismatic axially loaded members. Okay. Also, I remember that we further learn how to calculate the total extension of tapered bars and bars with varying loads. Yes. I want you to take note that in this lecture, we will focus on how to calculate axial deformation of uniformly varying circular and rectangular bars. Okay, exactly. It is very important to note that in practice, not only prismatic members are used. Take note that it is very important to note that in practice, that is at the site, not only prismatic or not only uniform members are used. Hence, it is very essential to learn about how to calculate stresses, strains, and axial deformation of such members. Exactly. So for now, let's focus on analysis of bars of uniformly varying circular sections. Okay, let's look at the bars, that is this kind of bars. Okay, bars that are tapering. Okay, whose end are hot, circular. Okay, and so if we are looking at, let me say, the right side of this, then we can say that this particular end is a small circle, and then the other particular end becomes a big circle. So we can name this D1, and then we come and name this D2. Okay, that is this becoming the diameter 1 and this become the diameter 2. Don't get confused at all. Don't get confused at all. So this is the diameter what? 2. Exactly. Exactly. So let's read it. Let's read the heading one last more time. I want to draw your attention to something. They said that what? Analysis of bars of uniformly varying. Okay, you see that this is uniformly varying. Circular sections. Okay, so this is a circular section, but it is what? Uniformly varying, because the other end is big, and then the D2, which is the smaller end, is becoming small, which is also the other end is also becoming small. You see, that is why this circle is just a small one. Exactly. So let's proceed. That is, in other words, we are looking at uniformly tapering circular section. Okay, exactly. Let's consider a bar, okay, or let me say, consider a bar uniformly tapering from D1 at one end to a diameter D2 at the other end, as shown in the figure below. So this is the kind of bar I'm talking about. As you are seeing over here, this is the kind of bar I'm making history about. So as you can see, this kind of bar is in tension. Okay, yes, because the forces are moving away from the bar, we classify it as being tension. But if they were moving towards the bar, it would have been in compression. Because this is in tension, at the end of the day, our force is going to be what? Positive, as we learned the other day. So this is in tension, and this is the P. This is D1. I told you this D1 and D2 are the diameters. Okay, so D1 is the bigger diameter, and then the D2 is the what? Smaller diameter. That is just from here to here. Okay. So take note that dx is just the what? The diameter from the left end. Okay. Uh-huh. As simple as that. As simple as that. As simple as that. Okay. Uh-huh. So let's look at the abbreviation for some of these formulas, and then let's see how best we can accelerate. That is, we are saying that our P is our axial tensile load on the bar. Okay. Because it's in tension, that is why we are calling it tensile load. If it was in compression, we would have said, let me say, compressor load. Uh-huh. And then the L is the hot overall length of the bar. Okay. So that is why it's shown over here. Or better, so we can say that the original length of the bar. Do you understand me? Uh-huh. The original length of the bar. Original length of the bar. Good. Also, D1 is the diameter at the bigger end, and also D2 is the diameter at the smaller end. E is our Young modulus. As I told you, every material has a Young modulus. Okay, that is, every material has a number of load it can resist before what going to failure. So the Young modulus of every material must even be known before that material is being put into construction. So take the Young modulus, very, 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 very important. Take the Young modulus, very, very important. Okay. In other words, take the Hooke's law, very, very important. Finally, the dx is the diameter at a distance x from the uh, dx is the diameter at a distance x from the left end. Okay, at a distance x from the left end, or we can say at a distance x from d1. Okay, that is diameter 1. So that is, take note, if we want to know the formula that we can use to calculate for the total extension. Okay, that is the total change in length that can occur in such a bar. We can use this formula over here. Okay, so you can see these are all calculations to derive the formula I'm about to show you now. Okay, you can use this formula to calculate for your total extension. Okay, so this is the formula I'm talking about. That is equation 12. Take equation 12 very, 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 very serious. Okay, that is, we are saying that what our change in length, or our total change in length of the bar, is equal to what? 4PL all over pi times elasticity multiplying what? D1, the diameter 1, multiplying the diameter 2. This is a matter of what? Computation. If you are good in computation, this is not going to be a problem for you. On this note, I'll urge each and every one of us to see our colleagues that are very, very good in calculator. Okay, because if you are not good in calculator, you will struggle. This course is a matter of computation. Do you understand me? And this calculator, your ability to be able to use the calculator very well will also help you to be able to use the laptop very well. I don't know if you have been able to discover this. You realize that in most of the time when you're using a calculator, you have to press shift before you can activate most of the things on your calculator. It's the same thing on the laptop too. Sometimes you have to, before you can be able to even activate, like use capital letters and even certain commands and all that. Sometimes you also have to use the shift command. Do you understand me? We also have the alpha on the calculator. It works hand in hand and all like that. Okay. So you have to just learn, or to just adapt to the use of the calculator, so that life can become much more easier. In the world of science of technology, or most of the time, for you to say, in the world of AI, you shouldn't struggle with much things. Go to AI and ask AI, how can I save a word on my calculator? AI would have taught you and make you more history. Go to YouTube. How can I save 1, 2, 3, 4, 5, 6, 7, 8 on my calculator? YouTube would have taught you, and life would have become much more easier. How can I plot a graph? You see? How can I solve a quadratic equation with my calculator? YouTube would have taught you, or AI would have taught you, and life becomes much more easier. Yes, yes. So let's proceed. So this kind of equation, we said that we will solve what? A tapering hot bars that have circular ends. Okay, as if you're having a bar that is tapering like this. If you have a bar that is tapering like this, that is, let's say this part is circular and this part is also circular. Then at the end of the day, you say that this smaller end become your hot D2, and this bigger end become your what? E1. So we can use this formula to calculate for the what? Total change in length of the what? Bar. That is if it is being subjected to what? A force, okay? As it being what? A tensile force, or let me say a compression force. Okay. Exactly. 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 So this force could be P, this force could be P. Take note, the forces could also even be acting towards the bar. Yes, towards the bar. On this note, I continue to say that the laws of physics are the same for all observers in a uniform motion relative to one another. I sent a slide to your page today. I don't know if you have seen it. Yes, but if you have seen it, then it will really help you, because even in secondary school, SHS students are also learning elasticity. Okay, so if you in the university, you don't know anything about elasticity, or your idea on elasticity is even weak, then it means that even those small boys can catch you any day and whip you in terms of academics. Okay, which is very, very, very bad. So you should do well and what? Practice this very, very, very well. So that when you are good at it, one day, even when your siblings or even your child comes to you with a homework for you to do for him or her, you can be able to do it, so that life become much more easier. All right, let's proceed, let's proceed, let's proceed, let's proceed. So the formula I just showed you, also this is the formula over here. Someone is asking, why are we using pi over here? A very good question. Because of the reason why we are seeing the pi over here is that it's because of the circle. Okay, if this was a rectangular or having a square end, you realize that there would have been no pi. Okay, so the pi was as a result of the what? The diameter d1 and what? The d2, that what brought about the what? Pi. If they were not there, you realize that pi wouldn't have been introduced into the whole equation. Okay, thank you. That was also good, a very, very good question. Let's proceed. Let's also look at analysis of bars of uniformly tapering rectangular section. So you realize that this is also a different subtopic. We are looking at non-prismatic section, but we have already looked at analysis of bars of uniformly tapering circular section already. But in this case, you see where we are putting the main focus. Okay, we are putting the main focus on what? Rectangular section. So in that case, I'll highlight rectangular sections differently so that we can all understand things clearly. You see, on this case, we are not just focusing on anything but rectangular sections. So if that is the case, let me highlight here and let me make it differently so that you get a clear difference of the two. You see, the initial one I just showed you, that was this one that we have already spoke plenty about. You said that this one was circular sections. And now this became, so the first one we look at was, let's say, analysis of bars of uniformly varying circular section. Okay, but in this case, we are going to look at what? Analysis, okay, of bars of uniformly tapering rectangular sections. Okay, exactly, exactly, exactly. So we are saying that uniformly tapering rectangular section, that is, consider a bar, consider consider a bar of constant thickness and uniformly tapering in width at one end to a width B. Okay, let's take it one more last time again. Consider a bar of constant thickness and of uniformly tapering in width A at one end to a width B at the other end as shown in the figure below. Okay, so let me quickly highlight. This is what? To A and what? With B. Okay, at one end. That is what I'm talking about in the figure below. So this is with A, and this is also the with B. As we were saying initially, these are the forces that are acting on the bar, and these forces are in tension, as we can all see. Take note that this is the hot end of the bar, and then the end of the bar, you can see the with B. You see how it is looking like? You see how it is looking like? Exactly. So This is the face. You see that this is a rectangle, but unlike the other ones, it was having a circular end. If it was a circular one, it would have, here would have been named D2. Okay, but because in this case it's a rectangular end, that's why it has been drawn this way that you are seeing. Okay. Uh-huh. Unfortunately, for this was not produced. I'm going to produce it over here for you to see. So this end is going to look like something like this. You see, and the thickness is still the same thing. And the thickness is still the same thing as you are seeing over here. It's having a rectangular end. All the other rules factors are still the same. So from bx, okay, is just the distance from what? With a, that is the distance from the left side of the bar, okay, to the dx that you are seeing over there. Take note that P is the axial tensile load on the bar. L is the total length of the bar. Okay, this is the L, total length of the bar. A is the width of the bar at the bigger end. So you see the width of the bar at bigger end. This is it over here. That is the A. And B is the width of the bar at smaller end. The width of the bar at smaller end. This is it over here. The B as you are seeing over here. And E is our Young modulus. As I told you, every material has a Young modulus. That is the number of load it can resist before going to failure. Exactly. Finally, the Bx is the width at a distance x from the left end. Okay, so this Bx is the width at a distance x from the left end, as you are seeing over there. So to also know the formula that can use to calculate for the total change in length in what? Let me say prismatics, a prismatic section with a rectangular end. This is the formula that we can also adapt. Okay, so you can see so many formulas have to be proved to be able to obtain that. Knowing how to prove these formulas is also a very, very good thing and will go a very long way to help you. Because of time, we can't spend much time into proving those formulas now. Okay, so we say that this is the formula that we can use to calculate for a total change in length in a bar that is tapering and has a rectangular end. Okay, so in this case, we are going to use what? PL over elasticity times the thickness. Okay, multiplying the difference in what? Width. Okay, that is with A minus with B. Okay, all multiplying the log E of with A over with B. Okay, that is equation 12. Take it very, very, very serious. Take equation 12 to very, very serious. You can quickly jot that somewhere. You can quickly jot that somewhere. Very, very good. Very, very good. So, as I was saying, this is equation 12, as we are all still seeing here again. This is equation 12. This is the equation I'm still talking about, equation 12. So from here, I want to take some few questions even before we proceed. Please, is anyone having any question to ask? Is anyone having any question to ask? Any contribution to make before we proceed? Okay, Simon, Peter, kindly unmute
Okay.
and make us history.
Okay, please. In the formula for the analysis of bars of uniformly tapered rectangular sections, please start from the log E.
Okay. It is a standard that is being tested in the lab to be able to use to calculate for the total change in length of a bar that is tapering rectangularly.
Okay.
Okay. Mm.
Mm.
That's where that is coming from.
Okay.
Okay.
And the distance and the distance, the x and the dx, you were saying is from the left side to the distance to the thickness or something like that. I didn't quite get that, please.
Oh, okay. The dx is just the distance from the left side. Okay, that is the distance from diameter one. Okay, but if you are talking of it in terms of a rectangular one, then you say that bx is the distance from the width. Okay, that is the left side. So what I'm talking about or what you are referring to is this. You see, uh-huh. So this bx you are seeing over here is the distance from the what? Left side. So that is the bx. This is it over here, the distance. Okay. It is the width at distance x from just the left end. Okay, so this distance from here to here produce that you are seeing over there. Okay. Please, any other question? Are you okay?
Yes, please. Yes, please.
All right.
So the dx is the thickness.
Oh no, it's just the distance. Okay.
Okay.
Yeah, it's just the distance from
Okay.
one end to the other. Yes. Okay. Okay. So please, any other question? Is there any other question before we proceed? All right, all right, all right. So let's quickly let me talk about this and let's proceed. So at the end of the day, prismatic section, we spoke about this in, let me say, lecture 3. Okay. We spoke about this in lecture 3. Do all to visit my YouTube channel. Do all to subscribe. Do all to like the videos and share comments to enhance creativity among others. So in lecture 3, we learned that to calculate for the change in length, we have to use this formula, that is PL over AE. Okay. Where we said that the P is our force, the L or the P can also be a load. The L is the length, A is the area, and then the E is the elasticity of the hot material. Okay. But in today's lecture that we looked at, we look at non-prismatic sections. Okay. We look at non-prismatic section. And non-prismatic section, we focus on two subtopics. That is one, we look at uniformly tapering circular sections and also uniformly tapering rectangular sections. Okay. We realize that to know the what total change in length, or let me say the change in length of a uniformly tapering circular section, we have to adopt the use of this formula. Okay, that is the 4PL over pi E D1 D2. Okay, and also to know the change in length. Okay, to know the change in length for a uniformly tapering rectangular section, we have to adopt this formula. Yes. Before we proceed to even solve some questions, I want to ask a question before we proceed. Please, where is the pi coming from? Where did I say this pi is coming from, and why was this pi adopted in this calculation? Simon Peter, kindly unmute yourself and talk to us.
Okay. So because we are dealing with circular sections, we have to find the area, and to find the area,
That
we are
is
going to use pi.
good. That is very, 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 very correct. Thank you very much for the wonderful contribution. So I said that it's because we are dealing with circles, or it has diameter 1 and diameter 2. It's giving us ideas of circle. That is why the pi is being adopted. So that was a wonderful contribution given by Peter. At this point, good students, you have